Recording started.
Good morning, guys. I hope you're doing well today. You too. That's kind of how I feel today. It's kind of gloomy out here, kind of rainy. Although when I hear rain, I think spring, so that's exciting because, I'm totally ready for spring. I'm done with all the snow. But then I hear snow is in the forecast for Saturday, so I'm like, everyone in your house needs to go back to bed. We have mornings like that in my house too. That's right, Isaias. You have the really bad spring allergies, so I know you never look forward to that. I do, though. I don't have that bad of allergies, so I look forward to it. See, with the warm weather yesterday, we have parts of our lawn starting to show, and the dog is already starting to dig holes in the ground, so we're like, no. So, not looking forward to that whole side of things. So we definitely have a dog that's a digger. Like, she'll just dig holes like nobody's business. So not looking forward to that because we got to escape that for a little bit with the frozen ground and the snow cover. But oh well. All right, so you're probably wondering what's on the agenda for today. We do kind of have a work day. Tomorrow is a no school day. Woohoo! No school for you guys. Um, And so today is kind of just a work day because 6.06 was a very heavy lesson. There were a lot of kind of complex concepts, so to speak. We may have gotten lost in the mix a little bit. So I want to start off today by just taking a look at some corrections from the 6.06 homework assignment. I know that there are three questions for sure that I want to look at. But then we can open it up for any other questions that you guys might have, not only on 6.06, but any of the previous lessons as well. All right, so let's start. If you need to do corrections on 6.06, now's kind of your opportunity to grab those. So when I put them on the board here, you can either screenshot them or write them down yourself in a Google Doc or an email, and then send me that Google Doc or email today sometime, and you can get half your points back as far as those corrections go. Okay. Does that sound good to everybody? So starting with the 6.06 lesson, then kind of working backwards from there. Okay, if we finish early, like you guys run out of questions to ask, that's fine. We can wrap up class early. I'm sure nobody will be opposed to that. But I for sure want to hit a few of the questions from the 6.06 lesson for sure. The first question I want to look at is actually number 1. So I got the old PowerPoint up from Tuesday's class to kind of help us as a guide or use that as a guide. Okay, instead of doing the examples though, obviously we'll just take a look at the question. So question 1, it says express the complex number in trigonometric form. So this is a complex number, but technically we probably should add in the missing imaginary term of it. So a complex number, remember, has a real part and an imaginary part. So technically there's a 0I that's behind that -7. So when we go to write this in the trigonometric form, we have to find r and we have to find theta. So let's start by finding r. So remember, to find r is a lot like the magnitude. You're going to take each coefficient of each term and square them and add them together. So a squared in this case is our -7. And b, oops, sorry about that, is our 0. So what is r going to equal after I simplify that? Yeah, it's going to be a positive 7. All right, so, and we kind of knew that looking at all of our answers here, that we knew r was going to end up being a positive 7. What we have to be careful of is the theta. So theta, it can be found using this tangent theta equals b over a. And we know that we're going to have to do the tangent inverse to get that theta by itself. So in this case, what is b over a? Looking at that complex number, 0 over negative 7. All right, now let's think about this on the complex plane. So on the complex plane, negative 7 plus 0i is somewhere over here, right? So we need to then figure out what is going to be the tangent at that spot. Or we can then look to see what is the degree measure over at that spot, right? Not necessarily what tangent might be, but what is that degree measure? Because tangent of 0 over negative 7 actually leads you to this spot itself. So I think this is where a lot of people got confused, is how they could find that theta. So when I take a look at tangent of 0 over negative 7, well, negative 7 isn't on the unit circle, but negative 1 is. So where does tangent equal 0 over negative 1? That's out over here by pi, right? I think everybody would agree that that's over at the pi location. And we can see that on that complex plane if I were to relate this back to our unit circle. This is that pi location. Well, we don't have our measurements in radians, but we can convert that to degrees pretty quickly. Pi is the same as how many degrees? 180. Yep, so we're going to want to choose the option where theta is 180 degrees. So we really got to kind of pay attention to where the point is falling in the complex plane to help us identify what that theta is going to be. I saw a lot of people choosing 0 because 0 over negative 7 is just a 0. But remember, we got to relate that back to our unit circle. So where does tangent equal 0? Well, tangent equals 0 at pi and 2 pi, and we needed the pi location because of where the original complex number was occurring. Okay. Questions with that one at all? Hey Rebecca, we're just going over some of the questions from 6.06. So we just got done with number 1, and we're going to take a look at number 2 next. Number 2 was very similar to number 1, and I think now that we've seen this first one kind of explained, hopefully number 2 we'll be able to figure out what that theta is going to be a little bit faster than maybe we did with the question 1. All right, so again, I noticed a lot of errors with being able to pick out what theta was. Technically, if this is a complex number, what is the real term of this complex number? 0, right? So technically, it's like a 0 plus 3i, if I put it into that format. Finding r, I think everybody was good in knowing that r was going to come out to be a 3. And really, that was the only option we had in our choices anyway, right? But we can see that that is going to hold true, that r will be 3. Theta is where the problem came in again. So we're going to do tangent inverse. This time, what is the b over a? 3 over 0. All right, so 3 over 0 is occurring where on the unit circle? So think about it. Where does tangent equal a positive number over 0? And there really only is one location where that's occurring. At pi over 2. Would everybody agree with Isaiah's pi over 2? If we think about it, and I go and I plot this on my complex plane, 0 plus 3i, that's like the point 0.03. So technically that is falling on the y-axis there, or technically the imaginary axis at 3, which is going to be equivalent to that pi over 2 location on your unit circle as well. Pi over 2, though, we don't have our choices in radians. We got to convert that to degrees. So pi over 2 is the same as how many degrees? 90. Yeah, and because we don't have 3 on the unit circle, what you would technically think about in your mind is 1 over 0, right? Because technically that's just a multiple. 3 is a multiple of 1. So we can convert that back to the 1 over 0 location on the actual unit circle to find that pi over 2 spot. It's just out a couple times around, right? So if you think about the unit circle, it's just wrapping around 3 times before you get back to that spot. But it is equivalent to that. So we are looking for 90 degrees, which means the last choice is going to be the one we go with for our trigonometric form. Any questions with number 1 and number 2? Because those are finding theta. That was the part that I noticed a lot of people were kind of making a mistake with. We weren't able to convert that back to kind of our complex number and look at that in the complex plane and making sure we were grabbing the appropriate theta based on where it fell in the complex plane. Okay, the last question I wanted to take a peek at from this lesson was the last one. I think that was number 6. Of course, we didn't get a lot of time to look at, oh, I gotta say the guy's name, the Moivre's theorem. I'll get it one of these times. But basically, what his theorem stated there, oh, and it wasn't even that, is finding the nth roots of a complex number, so I apologize. So question 6 is kind of looking and similar to this last example we went through, but we did go through at the end of class on Tuesday, so we went through it pretty quickly. So let's go ahead and take a look at how this is going to relate back to the finding the nth roots of a complex number. So this is asking us to find cube roots. So how many answers am I technically going to have in question 6? You're going to have 3 answers, right? Because the cubed root means that n equals 3. So when n equals 3, you should have 3 different answers here. All right, let's go ahead and actually apply our formula from up above. So we got to start with figuring out what is this number out in front of our parentheses. So in our case, it's going to be the cubed root of 27. And this does work out nicely for us. What's the cubed root of 27? 3, yeah. So we're going to start each of our answers off with a 3 out in front of that parentheses. Now we do want to start with k equaling 0. We'll search for k equaling 1, and we'll search for k equaling 2. So this is where our 3 answers are going to come from. Now it's nice because they're working with degrees instead of radians. So when it says to add 2 pi k, what technically is 2 pi in degrees? 360, yeah. So we're going to work with the 360 in our formula times k versus that 2 pi times k. So a little bit nicer for us there. So let's start off It says cosine of theta, so that was our 279, plus 360 times k. Well, k is 0, so technically you're just adding a 0 on there. And we have to divide by n. Well, n we said was 3. So let's go ahead and simplify this, and I'll write my final answer kind of at the end here. What is going to be this first degree inside? So 279 plus 0, all divided by 3. A 93 it comes down to. Okay, and then obviously it's going to be the same for our sine. Eeks. But there is our first root, right? So that first answer that we're looking for. All right, the second answer is when k equals 1. So following suit here, we are going to change things a little bit, right? Because now we're going to have 360 times 1. Well, that's just your 360. Let's simplify what we get inside now for that second degree. What is 279 plus 360? And then all divided by 3. A 213. Good, so there's our second answer. And then the third answer comes when k equals 2. So technically we'll get a 279 plus 360 times 2. Well, 360 times 2 is a 720. What does that simplify then inside there? A 333. Okay, so we'll have cosine of 333 degrees plus I times sine of 330. Yep, and you'll notice that pattern. It's a little hard to establish if you have just a small amount for n, but you should notice that you're adding kind of that same amount each time. So in this case, it would be that 120 that you're adding each time there. And if you had to go more, you could use that pattern to help you find the next theta or the next degree as you progress through those k's. The more k's you have, the smaller the amount should be that you're adding each time. So if k would have been 10 here, we would have had a much smaller number that we're adding each time in between our jumps. It wouldn't have been so large like the 120 was. All right, questions with the last one there? If you had added 2 pi and then 4 pi, no, it would not. The only thing though is that you'd want to convert your 279 into your radians. So we changed it to degrees versus radians because that's what we were given to start off with. So if we were given a measurement with pi in it as our starting amount instead of the 279 degrees, then we definitely would have added the 2 pi, and then we definitely would have added the 4 pi. It should not change your answers though if you're converting the 279 degrees to radians first and then going that route. So you should still end up with the same amount or the same answer in the end. Good. Any other questions regarding this type of setup here, or like we had in question 6? Okay, now that we saw 1, 2, and 6 worked out, were there any questions on 3, 4, or 5 from the assignment that you wanted me to look at? So any questions from number 3, 4, or 5 of this lesson? Okay, those were kind of the more complicated problems that I had noticed. 3 is very similar to 1 and 2. Make sure you're looking for the right theta based on where that complex number falls in the complex plane, right? So as long as you're keeping an eye out for where that theta should be in the complex plane and the unit circle, I think you'll be okay. All right, so if there's no other questions from 6.06, did anybody have questions that they wanted me to look at from any of the other previous lessons? So maybe 6.05, 6.04, anything from those that you want me to review? Okay. Yeah, so there was a question pop up going back to 6.02. So I know most of you are good, but it's always good to refresh some of those beginning lessons as well. So let's take a look at question 2 from 6.02 and see what we can come away from there. Yay! Way to go, Isaiah. That's exciting. All right, so 6.02, I'm going to grab the book for this one. We need our projection. So does anybody have... Oh, that's always the worst when you're waiting for your professor to like grade your work. I think that's why I'm so fast with grading homework because I always hated the waiting aspect of it all. I had one professor in college that would never return any tests or papers or anything. So you never knew where you were sitting in the course. And I think that's when I vowed to myself I would never be that type of teacher. So that's probably where I got my OCD from is having professors that never returned graded papers. It was a mystery. Yep, you had to go speak with them individually during their office hours and ask for your grade to know where you were at. If you didn't take that initiative, you wouldn't know. Kind of scary, huh? Okay, so we're looking at a projection of U onto V. All right, so I grabbed this formula back from 6.02. It's been a while since we've seen it. So always good to kind of refresh before we go into a test next week. And we do have a test next week, but Tuesday I'll spend some time reviewing with you guys some of these earlier concepts again. I think I have a Kahoot! It game planned for next week, Tuesday, so that'll be a little fun. And then we'll dive into the next unit, I think next week, Thursday, we'll finally start Unit 7. So we do have a little bit of time here to help us prepare at the end of Unit 6 because there were some hefty concepts in Unit 6 here with our vectors and our parametric equations and polar equations and our complex numbers as well. All right, so projecting one vector onto the other, we need to start with the dot product of the two vectors. So in the numerator here, we're going to start with the dot product. Let's go ahead and see if we can remember how to do that. So the dot product, remember you take the first two components, multiply them together, and add it to the second two components multiplied together. So what is the dot product actually going to be here? Yeah, just a 3, because you'll have a 3 halves times 2, which the 2's cancel off and you're left with just a 3. And then you have negative 3 halves times 0, which is just your 0. So we do end up with the dot product of 3 for the kind of numerator of that fraction. In the denominator, we're going to take the squared of the magnitude of vector v. So let's find the magnitude of vector v. So what's the magnitude going to be there of our vector v for starters? A 2, right? Because we get the square root of 4, which is just a 2. And then in our equation, it looks like we're probably going to have to square that, right? So 2 squared is going to be a 4. All right, then we got vector v kind of hanging out at the end over here. So we're going to multiply that 3/4 through the vector. So let's see what we get when we distribute that through the vector v. So what is 3/4 times 2? A 6/4, which is 3 halves. And then the nice one is, the second one is nice, right? Because 3/4 times 0 is just your 0. So I believe that's going to match up to our choice A, a billion zeros. All right, 0 billion is not wrong, right? Technically. Awesome. Okay. Anything else from kind of these beginning units? Like I said, if there was any, you can use these as corrections if you need to. So this was 6.02, number 2. If you need to screenshot that and submit it because you got that one incorrect the first time around, this will count as corrections. All right. Anything else? I know a lot of you said you were good. But if there is anything, now is kind of the time to ask. That's too funny. Yesterday, my dog Penny was sitting in the doorway while I was teaching, and she just stared at me for like 5 minutes straight at the start of my class. And I was like, okay, that's a little creepy. You can stop staring now. She eventually, I think she got bored because we were talking, what were we talking about? Oh, exponential functions. So we were talking about exponential functions. She got bored and laid down. I think she's like, this is boring. 6.05. Yep. I've just gotta, it takes me a moment just to pull these up. My computer is not the fastest, so I should say my internet's not the fastest. All right, now I'm going to go back to 6.05 and we're going to find our Limacon curves because there should have been a chart for us to kind of to follow with those Limacon curves, and hopefully that chart will help us determine what that equation is going to be from down below without necessarily having to refer back to the graphing calculator to find the correct equation. So I think the first thing, when it's on page 498, I wonder, oh, I just closed out of the ebook that I have for this class. Let me see. Give me 1 second and I'm going to see if I can go grab this Limacon curve kind of chart for us. In the meantime, if you guys want to look at page 498 in your book, that's where I'm pulling it from. Probably would have been faster for me to go to the online lesson and steal the graphic from there. All right, so the first thing we're going to look at is the symmetry, and then hopefully we can maybe narrow down based off of the maximum value if from there. So do we have symmetry about the y-axis or the x-axis occurring here? We definitely have it about the y-axis, so that's going to narrow it down to our sine function, which I guess didn't really narrow down our choices at all too much. Let's see what the range might be. Well, I don't even think that's going to help us. Maybe if I should have a plus or a minus sign in there. Let's see. It's a little hard to distinguish what the maximum is going to be. If I'm guessing that's probably a 4 in there, right? From here, because we didn't really establish between the plus or minus with the analyzing a Limacon curve, let's go ahead and see I'm just taking a look at some of my options real quick. 1 sec. On the top of that page, they give us these different types of Limacon curves, or I'm thinking we can use this chart right here to help us identify maybe the A and B values that we're looking for. Because notice how they have like A over B. If that's less than 1, then you're getting this inner loop. Obviously, we want something like part B occurring. That looks more like a cardioid. That's what we kind of got going on. So we're going to want the A and B values, I think, to equal 1 in this case. Yeah, so I'm thinking it's going to be either choice 1 or choice 2. And now we just have to decide on if it's a plus sign or if it's a minus sign in there. So at least we got it narrowed down to one of those choices. And let's graph it. I know it says possibly. Let me graph it and see. I know it says not to graph, but let's just graph and see what the difference is actually going to be between using a plus sign and using a minus sign actually in the equation. So I know it says not to graph it, but let's just do that to test it out to see if we can come away with similarities or differences between using a plus sign and using a minus sign in the actual equation itself. So we are working in, this is polar mode, right? Yep. So we got to make sure that our, oopsie. our mode is correct to begin with. So make sure you change that mode to polar mode, right? And then let's just graph the two and see what the difference is. So I'll do the 2 minus 2 sine theta, and then we'll do the 2 plus 2 sine theta for those r's, and let's graph and see what the actual difference is going to be. It looks like how it's going to open. It looks like one's going to open on the top and one's going to open on the bottom, right? So that's kind of like my weird shapes there. Two plus 2 sine theta is above it, so majority is above it. It's kind of reflected, it looks like, about. And then the minus sign is below. So we're definitely going to want to use the minus sign in this one because it is below, majority of the graph is below that x-axis. So it almost seems like it's kind of a reflection piece about the x-axis if you're using a plus or minus sign. It is, right? That's exactly what it seems like is going on. So in this one, we definitely want to go with option A. So essentially, if we're using a plus sign, we're going to think that our graph is going to be above the x-axis more. So here's kind of what I'm picturing going on, something like that, right? And then with that minus sign, it's kind of reflecting it, and we're getting it below that x-axis. Yeah, so technically we needed to graph there because that wasn't addressed anywhere, at least not that I found. I couldn't find where that was technically addressed in the actual online lesson there. So we needed to test that out and come away with our own understanding moving forward. So what I would do if you had this pop up on your test is we should be at least able to narrow it down using kind of those A over B ratios that we saw for the 4 different types of graphs. And then now we kind of know what to expect for a plus versus a minus. Yeah, seems to be. Yeah, so that was a good question. .01. Yep, and this will probably be the last one that we have time for today. Time flies when you're having fun, right? Number 5. Tommy, was that good for question 2 for that one before I ditch out on it? Okay, good. All right, going back to question 5, not question 2. 6.01 all the way back to the beginning. Ooh, this was a fun one. All right, so we need to make sure we're going to be in the correct mode for this one as well. Otherwise, we're not going to get the correct answer or output if we're not. So I think I saw a few errors because people were not in the correct mode and they missed a negative sign in the process. So this is kind of a lengthy one where you have two forces acting on each other, and you have to refine that resulting force with the magnitude and direction then. So we're going to find the two component forms of the vectors they mentioned to begin with. The first one has a magnitude of 200, and it looks like it has a direction of 60. So we're going to go ahead and just find the component form of this first vector. So take your 200 and multiply by cosine 60, and then the same thing, 200 times sine 60, and that's going to get us the first vector. So again, we have to go back to our mode, make sure we're in degree, and we're going to want to put it back to our function, right? Because now we're working with just our normal function there. Although I don't know if it would necessarily make a difference if you left it in polar. So you get, what is it, 100 for the first one? And is it like 173.21 for the second? Good. Now we're going to do the same thing with that other one. So we have a magnitude of 100, and this is acting on with the direction of 170. So let's put that into component form next. All right, what are we going to get for the second vector then? And right here is where a lot of people miss the negative. They put just a positive 98.48. You should get a negative there. All right, the resultant, if they're acting together, you need to add your two vectors here to get the resulting force, right? So what do we get when we add these two vectors? (1.52) 190.57. All right, now that we got the component form, we can find the magnitude and then the direction. So the magnitude of this, and I'm just going to call that vector v, I guess. You're going to square both components and add them together and take the square root. And that's supposed to be a 2, not a plus sign in there. Whoopsie. Thank you, Isaiah. So Isaiah has got the answer there, which is kind of weird because it comes out so similar to that second term, right? It kind of makes you double guess yourself for a moment, but it is 190.78. And then to find the direction, remember we're using tangent theta of b over a, so 190.57 over 1.52, and you're going to need to take tangent inverse of this fraction here. Oopsie. In order to get your theta. I believe that comes out to like an 89, yeah, 89.54. Which makes sense because this is in quadrant 1, right? So that would fall kind of in quadrant 1, and so does that theta. It's almost 90 degrees, almost hits that y-axis, but so it does work out. Good. That was kind of a tough one because we had to first put them both into component form, and then we knew we had to figure out we had to add the two vectors together after that, and then find the magnitude and direction of that resulting vector. So that one was kind of a lengthy one. But it's a good one to wrap up with. So we hit a little bit here and there throughout the unit. We'll practice more with Unit 6 in Tuesday's class. So we'll do our review game then. And then hopefully you guys will feel really good going into that Unit 6 test next week. And then I think we are beginning Unit 7 next Thursday, I want to say. You'll like Unit 7 too, I think. There's a lot of algebra behind Unit 7. All right, so that's all I got for you guys today. Remember, everything we did here today was fair game as far as corrections go. Just make sure you email me the work or the Google Doc where you collected the work so that I can go back in later this afternoon and then start adjusting those scores for the corrections. All right, that's all I got for you though. So I'll let you go. Have a great 3 day weekend. No school tomorrow. Woo-hoo. And I'll see you guys all again Tuesday. Bye, everyone.